Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to provide examples of finding shear and bending moment functions. So what we're looking at here, we've got this beam with the external loading shown, this 12 kilonewton force down and this 9 kilonewton per meter distributed load here. The first step typically in analyzing a beam is to find the reactions. I've already done that as I didn't think it needed to be part of the video here. 15.7 on the left hand, 23.3 vertically on the right, which I've called AY and BY. And now what we're going to do is we want to cut this system apart. Now, something about this beam here, we have a load change here. So we're going to do one cut kind of in this region where this is going to be X. But because we have a loading change here, we're going to have to do another cut in this region where this will be X. And then there's another change in loading here at this region. So this beam is going to take 3 cuts. So for the first part, this is going to be X, and then this is going to be X, and then this is going to be X. So taking them one at a time. So we're going to imagine now cutting the beam here at a location X. Now what I'm going to do is use this this guy here. So again, I've got to imagine cutting this beam at kind of an arbitrary location. I'm going to go ahead and draw a picture of it over here. And I'm going to draw a free body now of this beam. This is going to be a nice, easy free body. If we cut it here, there's no loading on top. We've got this force AY of 15.7 kilonewtons vertically. Then again, at our cut here, we're going to have an internal shear and bending moment. And because there's no other X forces, there's no reason to put a normal force here. All right, now we can now write equations for our free body. Sum of all forces y direction equals 0. And that's going to be 15.7 kilonewtons minus shear equals 0. So our shear force is 15.7 kilonewtons, and it's constant, not changing in this region. We can now write a moment equation, sum of all moments. So I'm going to go ahead and do the left end. Has to equal 0 with counterclockwise positive. Now when we sum moments about here, this force goes right through that point, nothing to worry about. This force does. The shear force here is creating negative moment, so we're going to have minus the shear, which is 15.7 kilonewtons, times, and again in this picture, this distance is X. So that's the moment produced by the shear force, right? Then we're going to have plus the internal bending moment, and that's it, equals 0. So our moment is equal to 15.7x, and that would be in kilonewtons. The 15.7 would be in kilonewtons times x. That's going to give us units of kilonewton meters. All right, so we can go ahead and kind of start sketching here. Out to 1.5. Our shear is constant at 15.7. And again, I'll just put these are in kilonewtons, and over here these are going to be in kilonewton meter. Constant shear up to that point. And you'll notice that we have a linear bending moment. This thing goes through 0, 0. And if we run that to x equals 1.5, whoops, if you give me a moment here. Okay, so I get about 23.55, 23.6. So I'll just put that point right here. 23.6 kilonewton meter linear function out to that point. All right, so first part, and this is the easiest part, is done. Next, get rid of all of this. Now what I'm going to do is I'm going to do a cut in here somewhere because the loading changes at that 12 kilonewtons. So I'm going to cut it maybe about here, draw myself a new free body. This little computer dealy works great for this. So it doesn't really matter where in here. That's going to be kind of an arbitrary location. All right, so now, free body diagram, we've got our force AY here, which is still the 15.7 kilonewtons. This 12 kilonewtons is now part of this load. No other loading in here anywhere, but at our cut here, we have the internal shear and bending moment. Again, applied at that point. We can get the shear from sum of all forces y direction equals 0. That's going to be 15.7 kilonewtons minus 12 kilonewtons minus shear equals 0. And that's going to give us, we just add that to the right, 3.7 kilonewtons for the shear, and that's again constant. I'm going to go ahead and just sketch that. So this equation is going to be good anywhere in this region now. So the shear apparently falls off down to, maybe about here. And again, that value, 3.7 kilonewtons. Not worrying right now that this is exactly proportionally correct. Right? Bending moment. Sum of all moments equals 0, counterclockwise positive. And again, I'm looking at this free body. So this force is going to produce a bending moment of minus 12, and I'm going to leave the units out. I'm just going to say note consistent units. 12 times 1.5. Then we're going to have the shear is going to produce a bending moment of minus 3.7 times the distance from here to here. And again, we're cutting this at an arbitrary location, so we're going to call that x. Then we're going to have plus the internal bending moment. And that's it. Everything's been taken into account, equals 0. So now our bending moment is going to equal, let's see, we would add this to the right and add this to the right. So I believe that is going to be 3.7x plus 18. Yep. All right, so we got a linear function here. All right, so this function is good anywhere from 1.5 to 3. So I'm going to go ahead now and put in 1.5 into that. All right, and we get 5.55. So this thing apparently is falling off here some, all the way down, maybe something like this. And I got that by putting a value of 3. Whoops. I think I did something wrong there. Let me do that again. All right, I'm going to put a value of 1.5 into this, and we're going to get, all right, 23.5. All right, so that's meeting up right where it did before. And now I'm going to put a value of, whoops. I'll back up and double check this. Again, I want to put in, all right, this function is good anywhere in this region, so I'm going to put x equals 1.5 into it first. Right, and I get 23.55. Okay, so we're meeting up here. And now I'm going to go ahead and put an x equals 3 into this function. We get 29.1. So if we get out to here, we're at 29.1. That's not much higher. And again, it's a linear function. Now the first function in this region, I believe, was moment equaled 15.7 x, and then you'll notice that the slope fell off, so that's why I dropped the slope a little bit when I sketched it. So this point again right here was 29. That's this point right here, 29.1 kilonewton meter. Okay, so I think we've got everything we need to know in this region. One thing I'd like to point out at this point, notice here if I differentiate our moment function, we get 3.7. Notice that the shear is 3.7, and in the previous example that was true as well here. We had, I believe, the moment was 15.7x, and if you differentiate it, you get 15.7, because this is a mathematical relationship that always holds. Your shear should always equal the position derivative of your moment. I usually use that as a check to make sure the work is working out well. All right, we get everything we need to know in this region. I'm going to go ahead and get rid of this. This work right here we don't need. Or this. All right, next. All right, now we want to investigate what's happening in this region, so I'm going to do an arbitrary cut somewhere in here. All right, so now where where we show the cut doesn't really matter. I guess I'll just do this. And again, from here to here is going to be x. So I'm imagining cutting this at an arbitrary x. And now I'm going to draw a free body. Okay, so the AY still there like it was before, 15.7 kilonewtons. This minus 12 is acting down. Now, here, what we're going to do is we're going to replace this distributed load with a single force vector. First of all, I want to take a moment and erase that. All right, we're not going to need this. We're going to replace it with a single force. The question is how much force and where does it go? Now, we cut this at an arbitrary x. So let me say that that's my cut. And that is x. This distance here would be x minus 3. So the area is going to be 9 times x minus 3. So the magnitude of the force I'm going to put in there is going to be 9 times x minus 3. That's coming from this distance, which is x minus 3, times this distance, which is 9 kilonewton per meter. Now, the location, where do we put that? Got to pay close attention to this. This distance right there is x minus 3. That makes half of this x minus 3 over 2. In red here, that distance is 3, plus we have to add half of that, and that was x minus 3 over 2. So that force vector is going to be down, and that's its magnitude, and it is at a location of 3 plus half of this. So that's going to be 3 plus x minus 3 over 2. Gives the location of the force vector under that little rectangular load. All right. Next, shear force, bending moment. And there's the free body of this beam cut at kind of an arbitrary location, right? And again, cut at an arbitrary x. All right, now to get the shear force, sum of all forces, y direction equals 0, up positive. So that's going to be 15.7 kilonewtons minus 12 kilonewtons minus 9 times x minus 3. For this guy, remember that was the magnitude of this force vector, minus the shear equals 0. So the shear is going to equal, I'm going to take a moment and pause this while I solve for that and make sure it's right. Okay, I'm back, and when we solve this for the shear force, here's where we got. And I want to talk a little bit about how I check these to see if they're right. If you put in x equals 6, because this function should be good anywhere along here, and I'm going to go ahead and put in x equals 6 all the way to the right, shear at x equals 6, you get a value of 30.7 minus 9 times 3. You get a value of minus 23.3 kilonewtons. Right? Now you'll notice this thing right here is equal to minus 23.3 kilonewtons, and that's curious, right? So if you were to draw a free body of just a sliver of this, and I'm going to go ahead and draw the sliver on the right-hand side. Here's what that sliver would look like. Now, if you draw the shear down as shown on the left, being consistent by Newton's laws, that would be this way. And we have a reaction this way of 23.3 kilonewtons, right, due to By. And basically, there's no distributed load over this, because this is, imagine this being basically infinitely thin. Let's imagine that being like a dx. There'd be no distributed load over it. Notice that the shear coming out to negative 23.3 means in this picture it's actually up, which means in this picture it's actually down, and notice that this thing is in equilibrium. So this matches the boundary condition on the right perfectly, so that function is good. All right, now let's work on finding the internal bending moment, again from this free body. Sum of all moments equals 0, counterclockwise positive. I'm going to do the left end. So if we sum moments here about point A, left end, this force doesn't show up. we're going to have minus 12 times the distance from here to here, 1.5. Then we're going to have minus 9 times x minus 3. Now the minus is coming because this force is producing clockwise moment. And then the 9 times x minus 3 is the force, and then we need times this distance. I'm going to put the distance in brackets. Now I'm going to probably shorten this a little. 3, and this is x over 3 over 2. Well, this is minus 3 halves, or minus 1.5. So we can write this as 1.5 plus x over 2. Right, and that's what this is, just cleaned up a little bit. 3 minus 3 halves is 3 halves, or 1.5, and then x over 2 right here. So this term is for the moment produced by this force about this point. Right? Minus, okay, then we've got moment produced by the shear force about this point. So that's going to be minus the shear force. And for the shear force, what I'm going to do is I'm going to put, whoops, that was a little longer than I thought functionally. I'm going to put minus 9x plus 30.7 times the distance from here to here, which is x. So this quantity represents the moment produced by the shear force. Right, then we have plus the internal bending moment, and then equals 0. Equation got a little long, sorry about that. So the next step here is to solve this equation for the internal bending moment. And what I'm going to do here is I'm going to take a moment and just pause this, do the algebra, and hopefully make sure it's right, and then come back. Okay folks, I'm back. So what I did here is I just distributed this and simplified and rearranged things, and there's a couple things I checked to see if I was right. Number one, look at this again. I go back to this element here at the right hand side. Imagine just a little sliver of this right hand side, and you'll notice that there's really no bending moment here. Again, this thing being infinitely small, the moment should go to 0 here. There's no moment here at all. If this thing were attached rigidly to something, there could be a bending moment at the reaction point here, you know, where this thing connects to the wall. But it's just sitting here, so there can't be a bending moment right at the end. So I tested my function by putting x equals 6 in, and out came 0 or something approximate to it. You know, I think I got like 0.3 or something. So I know it goes through this point, which is a good sign. This thing matches my condition at the end point spectacularly. If I put in x equals 3, I got 29.1 out of it. So this thing matches here. And because this thing matches the conditions, and if I check dm dx, it differentiates to minus 9x plus 30.7, I think we're in pretty good shape. All right, so this thing seems to match the conditions and the fact that when I differentiate it, I get the shear. You'll see the 9x term right there and the 30.7 term right there. So those things together, it doesn't 100% guarantee it's wrong, but if any of those failed, it would guarantee, I'm sorry, all three of those, matching the conditions at the endpoint and the differentiation, those two things together do not guarantee that function's right. But if either of them failed, it would guarantee it's wrong. But I find it highly unlikely that this function will match my ending condition here and differentiate this function and be wrong. So I got quite a bit of confidence in this. All right, now let me talk graphing. So here's my shear function. You'll notice it's linear. And if we put in x equals 3, that thing should give 15.7. Oops. All right, I want to plot this function here starting at x equals 3. Okay, 3.7, 15. Oh, yeah, 3.7 there. I read that the wrong spot. So this function matches up here very nicely. When we put in x equals 6, we get minus 23.3. So 6 minus 23.3. I'm not going to worry that we get this proportionally perfectly. This is going to do something like this, and it's linear. Okay, now I've already plotted points here and here. Now our shear, remember, is the derivative of the moment function here. So this thing is going to have a relative min or max at that point right there, because here's m, and then if I differentiate it, m prime, I'm going to get this thing right here. And by the way, if I differentiate that again, right, the second derivative of the moment, I'm going to get negative 9 out. So here, putting this together, here's what this is saying, that the first derivative of the moment function, right, is minus 9x plus 30. That's equal to 0 at that point right here. And it's real easy to solve. Just put a 0 here and solve for x. 30.7 over 9. That must be a relative extrema for this moment function. Furthermore, when we differentiate it again, I get negative 9 out of it. So since the second derivative is negative, that guarantees a relative maximum at that point. So my moment function here has a maximum here. Maybe it's up here, something like this, and we know it's quadratic. So this could be looking perhaps something like this. Okay. Real rough sketch, not perfect in any way, shape, or form, but I mean, that's the idea. I know I got a quadratic function that opens down. I know 2 points here and here. I don't want the video to get too long, so I think what I'll do is just talk about how I would find that point where the moment function is a maximum. Again, once you have this function, if you differentiate it, you're going to end up at the shear function. If you set this equal to 0, you would get the x value where this is a maximum. And then you can tell by the second derivative whether it's a max or min. If the second derivative is negative, that has to be a relative maximum. Once you found that value for x, you could just plug it into this function and get this value. But again, the video is at 22 minutes, so I think I'll just leave that as an exercise to the viewer. All right, so I hope this video demonstrates how to cut a beam apart in various locations to find functions for the internal shear and moment. Have a great day.